IGCSE Computer Science, Syllabus Statement 1.1.3a, show understanding that sound or music, pictures, video, text, and numbers are stored in different formats. So, there is honestly not much that there is to know here. We just need to know that they're stored in different formats. So, to make this video seem a little bit less boring, let's look at some formats. So for sound, we all know like MP3, WAV, AF, and M4A. I'm pretty sure all of you know MP3, at least. Maybe not these, but most of you should know MP3. Because most people store their music in MP3. Pictures is JPEG, GIF, TIFF, and BMP or BMP. I'm sure most of you know JPEG and GIF. Maybe not BMP. Video, MP4 is what we usually store our videos in. AVI sometimes, and maybe WMV. Text, well, we know about ASCII, and there's of course text files that pretty sure everyone uses. Documents, which everyone uses, Word documents. RTF, maybe. Now, numbers is a little bit different. It's sort of like, well, there's real, integer, currency, and date. Now, this is basically sort of like types of numbers. So like, a real is basically a number that can be that can have a decimal. So, for example, 19.8 is a real. An integer is a whole number, so it can't have a decimal. So, for example, 19. So it can't be 19.8 or 8.5. It has to be a whole number. Currency is, well, currency. And date is, well, date. So, yeah, sorry about this boring video, but I don't know why it's a statement, because everyone knows that files are stored in different formats. But to make this a little bit less boring, let's think about why they are different formats. Well, one reason is certain software uses certain file formats. So like, you notice sometimes that some apps that you may have on your computer can only open one type of file. And also, some file formats are better at certain tasks than others. So, for example, we all know that a GIF usually means that like an image that's sort of animated through a lot of frames that sort of loop. We know that. So, that's pretty much it. Sorry for the boring video. The next statement shouldn't be as boring. So yeah, that's it. IGCSE Computer Science, Syllabus Statement 1.1.3b, show understanding of the concept of MIDI files, JPEG files, MP3 and MP4 files. So, basically, this, well, I have to explain this. This is the third statement of 1.1.3, but this is the second video of it because the second statement was about error detection. So I just want to kind of go a logical order here, because the last video was file types. So this video is, file types, but more in depth and fewer file types that we have to cover. So this video is going to be more about, mostly about compression. Apart from MIDI, of course, which is all theory. It's more to do with compression. And I know that the fourth statement says something about compression, but we'll cover lossy and lossless compression there. So, yeah, let's get started. So, MIDI stands for Musical Instrument Digital Interface, and it's a widely used standard for interconnecting electronic musical instruments and computers. It's associated with the storage of music files, but MIDI files don't contain sounds. This makes them much smaller than other music file types. MIDI uses 8-bit asynchronous serial transmission, which means that there is a start bit and a stop bit. Now, this will require a bit of explaining if you haven't watched 1.2.1, which now, at the time I'm recording this, that is, doesn't exist yet. But it should when you're watching it. Well, eventually, if you're watching it soon, well, should exist. A MIDI file consists of a list of commands, actually, instructing a device which note to play and how loud to play it. That's pretty cool, actually. You just have a list of commands, like telling you which note to play, how loud, how quiet to play it. And, well, each command has a sequence of bytes. So there are three that we're going to be talking about. Status byte, which tells the MIDI device to perform a function. And the MIDI channel is also encoded in the status byte. So MIDI has 16 channels to operate from, and they're numbered 0 to 15, sometimes 1 to 16. And when we say a channel, we kind of mean like a medium of transfer. So you can imagine like wires, for example. So examples of MIDI commands can include note on or off, which basically indicates if a key has been pressed, and key pressure, which indicates how hard the key has been pressed. So like to sort of control the volume. So like the harder the pressure, the louder the volume. Then there's the pitch byte, which tells the MIDI device which note to play, and there's the velocity byte, which of course tells the MIDI device how loud the note should be played. A MIDI file has the extension .mid. This file can be played through a musical instrument. Now what makes MIDI special is, since it's a series of commands, it can be played through various musical instruments. Now that's pretty cool. So like if you imagine a normal MP3 file, like it just plays music, but the MIDI file you can play it through various instruments. However, music sequencer software is required to play the file through an instrument, as the file wouldn't be recognized on its own. So it's kind of linking to like how software can like only open certain files, like certain files can only be opened by certain software. It's kind of like that. So my chair has become really sweet. My square has become really alright, weird. JPEG. So look at these 4 photos of Mudkip, and you'll notice that as Mudkip goes right, he sort of starts to blur. Now this has to do with, well, the amount of pixels per centimeter. I'll explain this. Basically, this is the image that I got from Bulbapedia, the full-size image right here, which is 28.35 pixels per centimeter. That's 100% of the image. And then I've reduced it to 14.16 pixels per centimeter. So that is 50% of the original. And you can't really see it. It's like you can only see a really slight difference if you look carefully. Here you can see a little bit more. That's 25% of the original, and this is 10%, and this is most blurry. So when a photographic file is compressed, the size of the file is reduced, but the quality of the image is sacrificed for this reduction of size. Once an image is compressed, a new file is created which replaces the original file, which means that you can't really easily revert back to the original. So that's what JPEG stands for, and it will reduce a raw bitmap image by a factor of 5 to 15, depending on the quality of the image. Now, a raw bitmap image is basically can be a TIFF, which is spelled TIFF, or a BMP, which is bitmap. So bitmap picture or whatever. So this is kind of like the original picture. Like, so files of bitmap images basically tend to be quite large compared to JPEG, as JPEG compresses them. Now once we get to lossy and lossless compression, it should make a little bit more sense to you, but for now, let's just stick with this. I mean, I hope it kind of makes sense. So the number of pixels of an image is calculated by length times width. For example, an image which is 1,000 pixels by 2,000 pixels would be 1,000 times 2,000, which gives you 2 million pixels, as long as my calculator didn't screw up on me. The file size of an image is determined by the number of pixels, as well as the number of primary colors the image uses. Most images use 3 primary colors, red, green, and blue. So the file size of that image would be 2 million times 3, which gives you 6 million bytes, which is equivalent to that many kilobytes and 5.72 megabytes. How did I get these values? Just divide that by 1024, divide that by 1024 to get the megabytes. So here's a question. I put a little question mark there because it's a question. So an image is 128 by 364 pixels. Calculate the total number of pixels. Easy. Just times the two numbers. So we get 46,592 pixels. Calculate the size of the file. So remember that the image consists of 3 primary colors, we're assuming. So it would be this value times 3, which gives you that many bytes, and divided by 1024 to give you 136.5 kilobytes. So calculate the size of the JPEG file when it's reduced by a factor of 7. So when we say a factor of 7, reduced by a factor of 7, it's basically that divided by 7. So that gives you 19.5 kilobytes. So you might be wondering at this point, hang on, the exam is going to be non-calculator. So how the hell are we meant to do that? Well, I'll put it this way. We might be screwed, honestly. But I'm not actually sure. They might give you small numbers. They might be understanding, unless they're really cruel and they give you large numbers like the ones we were using. But hopefully it won't come to that. Hopefully we won't even get these questions in the exam. I say we, as in I'm about to take the exam in a few months from now. Although, by the time you're watching this, I've probably finished school, whatever, I don't know. Whenever you're watching this. So, MP3, Moving Pictures Experts Group 3. Okay, what are the experts group? Are they like the Illuminati or something? Alright, I have no idea. Okay, experts group, JPEG, MPEG. What is EG? E.g. Alright, so MP3 uses audio compression technology to convert sound into an MP3 format. This reduces the size of a normal sound file by around 90%, so basically a factor of 10. For example, an 80 megabyte sound file could be reduced to an 8 megabyte MP3 file, so that's 80 divided by 10. So a factor of 10. And this is done by removing sounds which humans can't hear. That's pretty cool. And this process is called perceptual music shaping. So here's another question. Music is to be stored on a CD. Each minute of music is worth 12 megabytes. Calculate how much space the CD would need in order to store 3 tracks, which are 3, 6, and 7 minutes long. So we add up the minutes to get 16 minutes in total. And then we times 12, because each minute is worth 12 megabytes. So 16 minutes times 12, which gives us 192 megabytes. The files are compressed using an MP3 compression algorithm. So calculate how much space the CD would now need. So we're assuming the file size is reduced by 90% or reduced by a factor of 10, whatever you want to call it. So 192 over 10 gives us 19.2 megabytes. So the CD has 800 megabytes of space. Calculate how many minutes can be stored on the CD. So remember that 1 minute is 12 megabytes. So we can have 800 over 12, which gives us 66.67 minutes. Or if you want to be accurate, 66 minutes and 40 seconds, approximately. Now this is the last thing, and trust me, it's really, really short. Like, it's actually just this slide. MP4 is a little bit different from MP3. rather than only music files, MP4, I thought it was, I'm going mad. MP4 can store multimedia files. So music, videos, and photos. Now, most people associate MP4 with videos, but that's not true. Apparently you can also store music and photos, although I haven't really tested it out yet. Could the course be a lie? Find out next time on Dragon Ball Z. IGCSE Computer Science, Syllabus Statement 1.1.3c, show understanding of the principles of data compression applied to music, video, photos, and text files. So, the thing is, I've covered compression with music, video, and photos already in another video. So the link for that will be somewhere up here. You can watch it. If I included it in this video, I'd be repeating myself. So it's just to save time and energy. So we're just going to be looking at lossy and lossless compression, as well as compression with text files. So let's get started. Lossless compression. In lossless compression, every bit of data is preserved when a file is compressed, and it's restored after being uncompressed. So this avoids data loss. So this is usually used for text files and spreadsheets, because we don't want to lose data when we compress a text file or a spreadsheet, because that would mean like a lot of errors. So like if you had a text file that you were, say, submitting to somebody or sending it off to somebody, and you compressed it and they uncompressed it, and it would like look kind of garbage, like really, you get what I mean, like data is lost basically. And same with spreadsheets, values can be lost. And also when you're compressing numbers, I'm used to saying compiling, when you compress numbers as well, we don't want to lose values. Lossy compression. With lossy compression, redundant information is permanently eliminated. So basically information that is redundant. So this can apply to photo, music, and video files. Now this is kind of like we discussed in the last video with perceptual music shaping in music files and quality loss in photo files. So basically redundant information, like in music, what we can't hear. So that basically removes that. Because if you lost important information, that'd be pretty disastrous. So let's look at text file compression. This video is going to be quite short, actually. So here I have a picture of Gandhi, because we're going to be using one of his quotes. So live as if you were live as if you were to die tomorrow. Learn as if you were to live forever. So this sentence consists of 74 memory units, including spaces and punctuation. I counted it myself. So to compress this, a compression algorithm can use a data dictionary to store repeated groups of characters in the sentence. So, like you can see, as if you were to, repeated. So we'll look at that now. So when the data dictionary stores these groups, it will replace them with numbers. So live, which is repeated twice, can be replaced with 1. As if you were to could be replaced with 2, and or from the tomorrow and or from the forever can be replaced with 3. So you'd end up getting something like this. This sentence, this new one, has 34 memory units, which is quite a lot less than our last 74. So this has saved around 54% of the original file size, which means that this is 46% of what we had earlier. That's quite a lot. So when the file is uncompressed, the groups of characters in the data dictionary are fetched, and they replace the numbers in the sentence. IGCSE Computer Science, Syllabus Statement 1.1.3d, Identify and describe methods of error detection and correction. So this video, as this says right here, we're going to be focusing on parity checking. And this is because, this video, that is, the entire statement is pretty long, all due to parity checking, which is the longest aspect of it. So I decided to put just this in one video and the rest in another, which is going to be the next one. So let's get started. So a parity check is a method of error detection and data transmission from one device or medium to another. For example, if a byte of data is transmitted, it would have a parity bit allocated to it before. Systems which use odd parity have an odd number of 1 bits. Systems which use even parity have an even number of 1 bits. To get a better idea, take this for example. Say you want to submit just this part, ignoring the red thing right here. So if even parity was being used to transmit this, the parity bit would have to be 0, as there's an even number of 1 bits already. So you can count them, 1, 2, 3, 4. So that's 4 1 bits, and 4 is an even number. So the parity bit here would be 0. If odd parity was being used, parity bit would have to be 1, as there is an even number of 1 bits. So 1, 2, 3, 4 plus 1 makes 5. And 5 is an odd number. And same with this and this. So hopefully you get the idea. Before data is transmitted, the sender and receiver of the data agrees on which type of parity to use. If a byte was sent from the sender to the receiver, and they both agreed on even parity, an error would be flagged if the byte had an odd number of 1 bits. This error is detected by the receiver checking the parity agreed and the number of 1 bits, including the parity bit, in the byte sent. So, for example, if you were to send this is the parity bit of course, and the receiver receives this, well, this is 4 1 bits, and this is 3, so clearly an error has occurred in the transmission of this. So the question might be in the exam, even parity is used. You'll always know what parity is being used, otherwise how can you do the question? Which of these bytes have been transmitted correctly? So this, and this. So let's count the number of bits here, and remember that even parity is being used. So 1, 2, 3, so that's 3, so it must be incorrect. 1, 2, 3, 4, so that must be correct. 1, 2, 3, 4, 5, 6, that's correct. 1, 2, 3, 4, 5, so that must be wrong, or incorrect. Yeah, incorrectly transmitted. And 1, 2, 3, 4, 5, 6, that's correct. And of course, this is 5, and that's an odd number. And this is 3, and that's an odd number, and the rest are even. But the receiver doesn't know which of the bits has been transmitted incorrectly. One way around this problem is sending a parity byte as well, and using this method, blocks of data can be sent. So odd parity is used here. So a parity byte is sent along with this byte being sent. And of course, this is the parity bit of this byte, and I've sort of made the parity byte stand out. So this was sent, but this was received. So where was the error? So what we do is let's look at the sent one just to get a better idea. So the parity byte is calculated by checking the parity of the vertical it's basically a vertical check, because the parity bit is calculated horizontally. So 1, 2, 3, 4. And if odd parity is being used, this would have to be 1 to make 5. But this is vertical, so basically sort of counts the, each bit column. So, for example, odd parity is being used here. So if there was 1 here, this could be 0. If there was 0 here, this would have to be 1, and so on, to get, odd parity, or an odd number of 1 bits. So if this was received, where would the error be? So what we do is count the horizontal first, or vertical, doesn't really matter. So 1, 2, 3, 4. So this row clearly has an error, because that's the only thing being sent. And we check the horizontal, or vertical vertical rows, or the columns. Yeah, I'm screwing up. The columns, we count the number of 1 bits in the columns. So this would be 1, 1, 1, 1. And now here we have 0 and 0. 0 here is classified as an even number, so there's the error right here. So there's an error with that bit. So let's look at an actual block to help you get the idea of how this works. So even parity is used, and this is sent. So again, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, and that looks all that looks all good. So let's count the vertical. 1, 2, 1, 2, 1, 2, 1, 2, 3, 4. So that looks all good if we count them up. So again, a parity byte is calculated using the columns of all the bytes sent. So since there's 1 here and even parity is being used, this would have to be 1. But this is received. So how do we find that? The error. So we count this again, and remember that even parity is being used. 1, 2, 3, 4, 5, 6. That looks good. 1, 2, 3. Here we are. With byte 2. That's where the error seems to be. So let's check where it is vertically. So 1, 2. That looks good. 1, 2, 1, 2, 1, 2, 3. Here we are again. So this must be the bit that's been transmitted incorrectly. So here's a question. Odd parity is used. Locate the incorrectly transmitted bit. So again, we count the rows. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3. And we don't include the parity byte because this is, remember, calculated from the vertical counts, so we don't have to count that. So clearly 6 is the only even number here, so it must be in byte 2. So let's find out which bit it is. So we count that should get 5. 1, 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3, 4, 5. 1, 2. Here we are, the 2. And this is 1. So it must be here. So this is the only even number here. So that must have been transmitted incorrectly. But what if an even number of bits have been incorrectly transmitted? Well, then there's no way of the receiver knowing, honestly. So, for example, take the byte 01010001, which has 3 1 bits. And that could be transmitted as 0000001, which is 1 1 bit, 2 bits changed. So, we know that, looking at this, that this is incorrect. This has been incorrectly transmitted. But how can the receiver know? Because there's 1, 2, 3, 3 1 bits, and 1 1 bit. So both the original and the altered bytes pass the odd parity check, because they have odd, they both have an odd number of 1 bits. So this is a limitation of parity checking, and that's why we need to look at other methods, which we'll look at in the next video. So for this question, there is really no way of telling. But don't say that in the exam if they ask you to find out which have been transmitted correctly, because you might not get the mark. But I'm sure they'll, they did, in the 2015 paper, they did actually ask why, what a limitation of using parity checks was. So, yeah, that's it for this video. IGCSE Computer Science, Syllabus Statement 1.1.3e, and this is the same as last time, but we're just going to be continuing this statement. So this video will cover, if I can remember, check digits, checksums, ARQs, and echo checks. So let's start with check digits. So a check digit is the final digit in a code calculated using all the other digits of the code. So they're used for barcodes, product codes, ISBN, and VIN. And they're used for identifying errors in data entry. So for example, a typo or a scanning error. So they usually can identify an incorrect digit entered, transposition errors, which basically means if you were to type in 2233, but you accidentally typed in 2323, the transposition would be the 2 and the 3 in the middle would be switched. So that's omitted or extra digits. So like if you were meant to type in a 4-digit PIN and you typed in 5 digits or 3 digits. And phonetic errors in speech. So like if you were to say the number 13, and so you said that like you spoke it, but then the computer thought you said 30, then that's it. It's a phonetic error. So an example of a check digit calculation is ISBN 13. So the last digit, the 13th, is calculated like this. So sum all the odd digits, excluding the check digit, sum all the even digits, and multiply by 3. Add the sums, and mod to get the remainder. And modding is basically getting the remainder of a division. So, for example, if you were to mod, like if you were to do 22 divided by 10, well, 22 divided by 10 would be, I'm just checking that on my calculator. I mean, I know it's 2.2, but I was just making sure. I don't know, I always have this, like, I always have to check before I say something. I mean, I know that it's 2.2, but I always have to check it. So yeah, it is 2.2. But it can also be said 2 remainder 2. So basically, 10 goes into 22 twice with a remainder of 2. So 22 mod 10 would just be 2. So if the remainder is 0, this is the check digit. Otherwise, subtract the remainder from 10 to get the check digit. So we'll look at an example. So calculate the check digit for this code. So an ISBN 13 code, ISBN 12 it looks like. No, but you have to, like the check digit would be right here, but we need to calculate it. So let's put it in a table, put the numbers in, and we're going to calculate the check digit. So we first add the odd numbers, and when we say odd numbers, we don't mean the odd numbers, we mean the numbers in the odd positions. So 1, 3, 5, 7, 9, 11, and, well, we're excluding this for now. So it's 1, 3, 5, 7, 9, 11. So 1 plus 5 plus 6 plus 3 plus 6 plus 3 gives 24. And the even numbers, or the numbers in the even positions, times 3. So it's 2 plus 4 plus 5 plus 5 plus 9 plus 6 times 3 gives us 93. And I double checked all of these, so they shouldn't have any errors. If they do, please, like, you know, keep in mind they put a lot of effort into these. No, they shouldn't have errors, hopefully. And we add them, the sums, and then we mod by 10 to get 7. And of course, since 7 isn't 0, we must subtract this from 10. So 10 minus 7 gives 3. So the check digit is 3. So let's try another one. Plug in the numbers. We'll whiz through this because, well, you know, you hopefully know the process of doing this. So there's this, and since this is 0, that's 0, so we don't need to subtract 10 from 0 to get 10. So just to keep in mind, with check digits in the exam, they won't expect you, I'm pretty sure they won't expect you to know ISBN 13. I'll double check that with the recent October-November paper, but what they'll do, or what they tend to do, what they still do hopefully, is they'll tell you how to calculate the check digit for a specific sort of number, so then you can work from the algorithm that they give you. So to check if an ISBN 13 code is valid, we sum all the odd digits, including the check digit, sum all the even digits and multiply by 3, add the sums and mod to get the remainder, and the code is valid if the remainder is 0. So let's give that a try. Is this code valid? Well, we got the check digit now, so it's 13. Plug it in. So 5 plus 5 plus 2 plus 1 plus 5 plus 2 plus 1 gives us 21. And 1 plus 4 plus 5 plus 2 plus 6 plus 12 times, or plus 6 plus 5 rather, I was reading this, times 3 gives us 69. And 21 plus 69 mod 10 gives us 0, so that's valid. Is this code valid? So do the same thing. So we get 19 plus 93, which mod 10 gives us 2, and so that's invalid since this isn't 0. So checksums are a little bit different. Now, this is another method of error detection in data transmission, just like parity checks. Now this method is a little bit more reliable than parity checks because, as we discussed in the last video, parity checks do have limitations. So here, data is sent in blocks, and at the end of each block, another value is added, and this is the checksum. So how a checksum is calculated? Well, it's a simple algorithm, so let's assume the checksum of a block of data is 1 byte, which gives us, gives it a maximum decimal value of 255, as in a decimal value as in base 10. So if the sum of the bytes of the block of data, the sum of the bytes of the block of data is less than or equal to 255, this value is the checksum. If it's higher than 255, then the checksum is calculated as follows. So divide the sum of the bytes of the block of data, we can give the value v, by 256, and we get the value x. Round x down to the nearest integer, so we round it down, which means that if x was, say, 7.3, or rather, actually let's think of a better one, 7.6 for example, we don't round it up to 8, we round it down to 7. So we basically get rid of what's after the decimal point. So then we calculate z using y times 256, and then the checksum is the original value v minus z. So let's take a look at that with the number 1223. So x is 1223 over 256. That gives us 4.78. We round it down to get 4, so we get rid of this. Then we calculate z, which is 4 times 256, and that gives us 1024. And the checksum is 1223, which is the original value, minus 1024, which gives us 199. And as you notice, that's under 255. So before a block of data is transmitted, the checksum is calculated by the sender and is sent to the receiver along with the data. The receiver then recalculates the checksum of the received data using the same algorithm and compares it with the checksum sent. Now, if the values are the same, then there have been no errors in transmission. If they are not the same, of course, the receiver sends a request to the sender to resend the data. So let's look at a question. Calculate the checksum of a block of data with the byte sum 1805. So it's good to get practice using this algorithm and to memorize it, because if the exam actually doesn't give it to you, then, well, you know, you're screwed. Also keep in mind it's a non-calculator test, so they shouldn't really give you really high numbers, and that's probably why they ask you to round y down, because you know, to make it an integer, so it's easier to work with. You don't have to times the... Yeah, okay, so we calculate x. So x is 1805 over 256. That gives us 7.05. And we, of course, round it down to 7. Then we do 7 times 256 to get z, which is 1792. And the checksum, of course, is the original value minus 1792, and the checksum is 13. ARQs. Now, coming to the slide, we're almost done with the video. We just have to cover 2 more things, this and echo checks. So an automatic repeat request, or ARQ, is yet another method of error detection in data transmission. If the receiver detects no errors in the data transmitted, it sends the sender an acknowledgement to notify them that the data has been sent correctly. An acknowledgement is basically a message sent indicating successful data transmission. If the receiver detects errors, it requests the sender to resend the data. If the sender does not receive anything back from the receiver before timeout occurs, the data is automatically resent. So that's basically, a timeout is sort of a set time allowed to elapse before an acknowledgement is received. And this will keep happening until the sender receives an acknowledgement. That's it. Echo checks. So an echo check is when data sent to the receiver gets resent back to the sender, which checks if any errors have occurred during transmission. Now that sounds a little bit stupid. Like imagine like a device sending data to another device, and that device resends it back so that it can check whether errors have occurred. Now that is quite, it's really unreliable. Because they don't know whether the error or an error has occurred during sending the data to the receiver or resending the data back to the sender. So when a device sends data to a receiver, or when a sender, like if your computer sends data to a printer, the printer will resend the data back to your computer so it can check. Like, what if the data sent to the printer was perfectly fine, but then when the printer sends the data back, there's an error? So what'll happen is it'll resend it, and then it's really, it's not really good. But if it is successful in sending and sending it back, then yeah, it's fine. But still, it's a little bit, yeah. So that's pretty much it for this topic, 1.1, and we're moving on to 1.2, which is the internet, or my friends like to say, the internet. A little bit more than the internet. It's about data transmission itself, as well as security and internet principles. So thanks for watching, and hope you find these videos quite helpful for your revision, or if your teacher forces you to watch them, or whatever happens. I hope you enjoy them. Hope you don't want to kill me, and thanks for watching.